My dear students, welcome again to the new class. In the last class, we discussed the cosets, definition of a coset, some examples of a coset. In the end, I defined that if G is a group and H is a subgroup of a G, and then we have to say that say A is congruent to B, and then we have to mod of H, then if AB inverse is the element of H. So we have to define this and we have to discuss some examples of in this case. Now today we have to continue this direction and we have to try to prove some properties of a coset. So first property of this coset we have to relate it to this congruent mod of H. We try show that this congruent A is congruent to B mod of H if AB inverse belongs to the H is an equivalence relation. So let if G is a group and H is a subgroup of a G, then the relation A congruent to B mod H is an equivalence relation. So if A congruent to mod, we know that A congruent to B and we have a mod of H, then we have to say that AB inverse is the element of H or A inverse B is the element of H. We have to show that this is an equivalence relation, means we have to show that this A congruent to B mod H is a reflexive, A congruent mod B is a symmetric. So we have to show that if we have to take any two, this means X is congruent to X of mod of H, then we show that if X is congruent to Y mod of H, then Y is congruent to X mod of H, that is a symmetric, this is a reflexive. Then finally we have to show that the if X is congruent to Y mod H, then Y is congruent to Z mod H, then we show that X is congruent to Z over mod H. This is called as the transitivity. So we have to show that if these three properties do hold, then we can say that this A congruent to B mod H is an equivalence relation. So let us start with the reflexivity. If X is the element of a G, then clearly if G is a group, then X inverse is also the element of a G. And if you know that by the property of a inverse, X inverse is equal to, you have a identity, and identity is the, because the identity element is unique for G and H, so identity is also the member of a H, and this implies that we can say that X inverse is equal to identity, this is the element of a H, so we can say that X is congruent to, by the definition we can say that we can like this, A congruent to B of a mod H, then we can say that A B inverse is the element of H. If A B inverse is the element of H, then we can say that A is congruent to B mod of H. So clearly X inverse is the element of H, that means X is congruent to X mod of H, that means this relation is reflexive. Similarly, we have to show that the second one is X and symmetry. Symmetric if X and X congruent to Y mod of H, then the by definition X Y inverse is the element of H, and because H is a subset of a G is also the element of a G, and this implies that because this is a group, so then we can say right, this can be right X Y inverse to inverse if we take is the element of a G, and if the element of a G, the inverse of this such element is also exists. If inverse of this element is exists, this means XY inverse is the element of inverse is also the element of a G, and this is the element of H, so this means inverse of this is also the element of H. We can simply say that like this, if X and XY inverse are the element of a H, so inverse of this XY inverse to the inverse is also the member of a H, and this can be written in the form of by the property of this AB inverse is equal to P inverse A inverse. This can be written as a Y inverse Y inverse ka inverse, and then X inverse, then X Y inverse ka Y is equal to Y, so YX inverse can be written in the form of this, and then means this is also the, and this is the element of H, so this means implies that YX inverse is also the element of this H, and as H is a subgroup. So if we have to just say that, so this means we can say that Y inverse ka inverse, X inverse are also the element of H. So Y X inverse is the element of H. So y is congruent to x mod of H. So we can say that this is clearly, we can say that y and x are the if x congruent to y mod H, then we can show that easily that y is congruent to x mod of H. So this means we can say that clearly this relation is a symmetric relation. Now we have to for this finally is a transitive relation. If x congruent to y mod H and y congruent to z mod H, then by the definition x y inverse is the element of H, y z inverse also the element of H. Now we have to show that x, this is the element of H, this is the element of H, x is a clearly is a subgroup, so is a closed, so x y inverse y z inverse is also the element of H because H is a subgroup. And if we writing this in the form of a, by using the element of this associativity x y inverse y and z inverse, and you know that y is the element of a H. So y this is giving you identity element, then we have to show that x and z inverse is the element of H. If x and z inverse is the element of H, so we simply say that x is congruent to z mod of H, and then finally it satisfy the transitivity conditions also. So this x congruent to y mod H satisfy all the three conditions. First is a reflexivity satisfy, symmetry is satisfied, and we have finally show that the transitivity is also satisfied. So we have to show that if all the three conditions are satisfied, that means a congruent x congruent to y mod H is an equivalence relation. So this relation we have to define, congruent relation is an equivalence relation. So what are the equivalence classes? The question is natural. We have to, if this is equivalence relation, then clearly what are the equivalence classes of this H? So equivalence class of x, we have to y is the element of H, then we can say that x congruent to y mod of H, or we simply say that xy inverse is the element of H. If x congruent to y mod H, then xy inverse that is there exists some H belongs to the H, xy inverse can be written in the form of this H, and because this x can be written in the form of H of y, then we define Hx is equal to in the form of a Hx, H is the element of H, then the equivalence class of this X is containing into the Hx. So clearly we have to starting from this equivalence class, and then we have to show that the equivalence class of X is containing into the H of X, and simply we have to again, if we are starting from the other hand, y can be written in the H of X, so y can be Hx is the element of H of X, then y of X inverse can be written as a H of X, Hx X inverse, and then by associativity Hx X inverse and Hx X inverse is equal to H is the element of H, and we have to taking the y is the element of Hx, and then we show that this element of H. So we have to starting from this, so y is congruent to this is the element of H. So we have to show that yx inverse is the element of H. So we have to finally show that yx inverse is the element of H. So y is congruent to x mod H. If y is congruent to mod of x, then H of x is equal to, we have to take a y is the Hx, and we show that y and x are y is congruent to x mod H. So thus Hx is equal to containing to this, and then already we have to show that equivalence class of x containing into the H of x, and then we have to show that Hx containing into the equivalence class of x. So by these two conditions we can say that equivalence class of classes are exactly of Hx. So we have to just say that if we have equivalence class of x is exactly what we have to write in the form of Hx. So now we have to just say that if H is a subgroup of a G, then for all x belongs to the G, Hx can be written in the form of this form. So Hx is nothing but is equal to G congruent to x mod of H. So now we have to just say that is clearly into this form. So every equivalence classes of this relations is the simply is a hx is the equivalence class of a x is the same as a h of x. So hx as h is a subgroup, then we can write hx as the element of a such type, g is the element of a g, and g is should be congruent with this h of x mod of h. So we will primarily focus on the right cosets of a subgroup. The properties of a left cosets analogous, and their proofs can be easily derived from the reader. So I will discuss only we taking the all the results for a right coset. Then you can just say that, and the similar way you can drive the proofs of this up to the in the form of a left cosets also. This run is a similar proof. We have to just say that in place of a right coset, we just take a left coset, and the proof we can prove both the similar fifty. So let us start as a very way, because if G can be written in the form of EG, and then EG is the element of a HG, E is the element of H, and G is the element. So this is the G is the element of HG. Every element of G belongs to some right coset, especially the right coset is the element. And similarly, G can be written as a G can be written as a G of E, and this is the element of a G of H. So this means this way we can say that the G can be also the element of a GH, and G is also element of a HG. So every element of a G belongs to some right coset, and similarly every element of a GR belongs to some left coset. So now a subgroup is always both a left and right coset is itself if H can be written as a EH and HE. So this means a subgroup is always is a right and left coset of itself. So this illustrates the simple fact that multiplying all elements of a subgroup by the identity, whether on the left or the right, does not matter the subgroup, because if multiplied by left or right, we have to getting the H itself is there. So now we have to just try to prove this theorem, and then we have to just. So let is saying that if G is a group and H is a subgroup of a G, we take G1 and G2 are the element of a G. Then he's saying that if G1 is also the element of a H of G1, it is trivial. We can just say that. Another property say that if we have a H of G1 is equal to H, if and only if G1 is the element of a H, and we have to, if we have a H G1 and the same as a H of G2, then if and only if we have a G1 is the element of a H of G2, and we can say that if H of G1, H of 2 is equal to the equal, if and only if we have a G inverse, G1 inverse G2 is the element of a H. And finally we show that G1H and is the same as H of G1, G1H and is equal to H of G1. Left and right cosets are the same if and only if we have a H is equal to written in the form of a G1H G inverse. So we have to prove this theorem, and that's a very important result for the. We have to start from the right coset, and then we have to similarly we can prove for the left cosets also. So starting with the first one is very trivial. You have a G1 is the element of a G, so we can write G1 can be written as a E times of a G1, and because E is the element of a H, H is a subgroup of a G. If H is a subgroup of a G is the element of H, then this is the element of a H of G1. So this implies this is the element of H of G1. So this implies that G1 is the element of a H of G1. So this is the proof one is very trivial. We have to prove into this one. Now second one is saying that you have to just set is a H of G1 is equal to H if and only if. So second one is say that H of G1 is equal to H if and only if we have a G1 is the element of H. Yeah, like this G1 is the element of H. Now, if we start in G1 is the element of H, then G1 can be written as a E of G1, and E of G1 can be, this is the element of a H of G1. Okay, so we have to just say G1 can be written as E of G1, and this is clearly the element of a H of G1, and then H of G1 is equal to, we have to is equal to H is given, and this implies that G1 is the element of H. So we have to calculate this is the element of a H, and then this is G1 is the element of a H of G1, and H of G1 is equal to H. So this implies that G1 is the element of a H. This is the first way we have to prove that if this is equal to this, then G1 is the element of a H is clearly. So this is very trivial. We have to write into this form. Other way, if we have to take a second one, we need to show that if G1 is the element of H, then H of G1 is equal to this. Now we have a G1 is the element of H, then G1 by showing the H subset of this, since G1 is the element of H, so G1 is the element of H. So now we have to take H of G1 is the element of H for all, for any H is the element of, because we have to just say that H is a subgroup. So H is clearly a subgroup of a G. Then if we take H of G1, then this H for some H is the element of H. Then we write H of G1 is G1 is the element of H. H is also the element of H. This whole completes the element of H. So clearly H is a subgroup, and subgroup is closed under the binary operation. So we can say that clearly this H of G1 is the element of this H. So for any H belongs to H, and then we have to taking the G1 is the element of H, and then we have to show that this means this are the element of H. G1 is also the element of H. So this means we can say that H of G1 containing into the this thing. So we have to just say that H of G1 is containing into the H1. Now we have to show that the reversely, then H can be written as a H of E, and E can be written as a G1 inverse. And now you have to just say that because H this G1 is the element of H, and this can be shown that this is the element of H, and this G inverse, and then this means G1 is the element of H. Then we can say that inverse of this is also the element of H, because H is clearly H is a subgroup. If H is a subgroup, means we can say that if G1 is the element of H, then G1 inverse is also the element of H. So we simply say that this complete element is the element of H. So if this complete element of the element of H, this is the element of we have to just say that can element of H of that is H of G1 is in H. So since G1 is the element of this, so this complete the by this H of G1 is containing H, and H is containing G1. By these two we can say that H1 G1 containing H, and then this also satisfy. So we can say that this hold for H of G1 is equal to H. Simply we can say prove this one. So this second one property is also hold. Now I will try to this third one property, where Hg1 is equal to Hg2 if and only if G1 is the element of Hg2. So now we have to try to the third one, and now since G1 can be written as, we have to try to prove this one, H of G1 is equal to H of G2 if and only if G1 is the element of H of G2. So first we take these are the same, Hg1 is equal to Hg2. So we take G1 is equal to, can be written Eg1, and this we can write in the form of a G, can be written in the form of A of G of G1, and then this is the element of H of G1, but H of G1 is equal to H of G2. This is the same as H of G2. This implies that this G is the element of H of G2, and then we have to show that this G1 is the element of H of G2. So fun part is a completely proof. Now reversely we have to just say that if you have a G1 is the element of H of G2, then you have to show that H of G1 is equal to H of G2, and G1 and G2 are the element of a G. So G1 and G2 are the, we have a G1 comma G2 are the element of a G, and then if G1 G2 are the element of a G, then its inverse is also the element of a this. So if this G1 can be is the element of H of G2, so G1 can be written as some H into G2, some H is the element of a H when G1 G2 are the element of a H. Now we can write, if we have to multiply by H of G1 can be written as H times H of G2, and then we use the property H of G2. Now H is the element of H, so H is also the belongs to the whole thing is equal to H. So this is giving you a simply is equal to H. This can be written as H of G2, so because f of H is equal to H is a H is the element of H is a subgroup. So by the property of a subgroup we can show simply this is hold again satisfied, this condition is hold for this result. So we proved that this theorems as three parts, and now these three parts we have to prove in this theorem today, and then in the next lecture we have to continue to prove the remaining two parts of this theorem and some other properties of a group into the next class. So I just stop today's lecture here, and after in the next class we try to prove these two results when Hg1 is equal to Hg2 if and only if G1 inverse G2 is equal to H, or we can say that G2 inverse G1 belongs to the H, and we have a G1H and Hg1 are the same, then H can be written in the form of a G1 Hg1 inverse. So this later on we have to show that this is again a form as a subgroup, and this is a special types of a subgroup. So now I just to stop today's lecture here, and then we have to continue for the next class. Thank you very much.